My dog Ruby and I were walking through the woods when we found a deer skull. I showed the skull to Ruby and let's just say she was a bit hungry. I mean, she even tried to eat this snake. Anyway, watching her gnaw on the skull got me thinking about chemistry. Because everything gets me thinking about chemistry. Specifically, how much calcium is in these teeth? And could I do a simple experiment to figure that out? The answer turned out to be pretty close to what textbooks say. But getting there was a lot more interesting than I expected. The root of the tooth appeared to be made of different stuff than the top part of the tooth. So I did my best to remove all of the root material. And the mass of the top part of the tooth that I sampled was 3.043 grams. Next, I put the tooth in a beaker and added some concentrated hydrochloric acid. You know, stomach acid. Except this stuff is hundreds of times more concentrated than the stuff in your stomach. I figured the acid would dissolve the tooth mineral, and this would release the calcium ions from the tooth. But do you see those bubbles being released? Yeah, I didn't expect to see any of those. That's because there's nothing in the main tooth mineral, called hydroxyapatite, that should release a gas in the presence of acid. But then I remembered that a tiny amount of carbonate sometimes takes the place of the phosphate ions in apatite. And sure enough, carbonate reacts with acid to form carbon dioxide gas. It's a bit crazy you can get teeth to behave like the baking soda and vinegar reaction. Anyway, after about an hour, the bubbling had almost stopped. But there was a color change in the acid to yellow. I'm guessing this yellow color came from amino acids found in the protein in tooth dentin. Regardless, when I came back the next day, the tooth was totally dissolved, except for some undissolved brown-black gunk. I have no idea what this stuff is. If you think you know what it is, let me know in the comments. I tried to remove as much of this junk as I could, but I couldn't quite get all of it out. My goal at this point was to get the calcium out of solution as a solid I could weigh. Sodium carbonate would do that. But first it had to neutralize all that excess acid, which released a lot of carbon dioxide gas. And because the acid I used was so concentrated, it released a ton of CO2. And I mean a ton of CO2. It also meant I was going to have to add a ton of sodium carbonate to neutralize all that acid. I decided to add some universal indicator to help me visualize when the acid was neutralized. You see that red color? Yeah, that tells us we got a long way to go. I added a little water to get everything more dissolved, and then continued to add sodium carbonate. And here's when I noticed that the carbon dioxide wasn't just causing bubbling, it was causing frothing. And that frothing tells us there's protein present in the mixture. The frothing caused a lot of problems. In fact, here's a failed first attempt I made on one of the teeth, in which the froth overflowed the beaker. I wondered if I could get the froth to dissipate by squirting in a little bit of ethanol. And sure enough, it collapsed the froth like magic. This went on for over half an hour, adding carbonate to neutralize the acid, followed by ethanol to keep the foam at bay. And then at one point, I noticed something really interesting. The mixture turned into a foamy rainbow potion. These colors show a pH gradient from acidic at the bottom to basic at top. I'm guessing carbonate reacts with acid mainly in the liquid below, but the foam above is poorly mixed, so it becomes depleted in acid. This allows more carbonate to persist as you near the top, and this raises the pH. Watch carefully here. You'll notice that the carbonate dissolves when it reacts with the acid. But check this out. When the acid is finally neutralized, a solid forms, and this time it stays. You can see this solid by noting the cloudy appearance that's in the liquid now. You can also tell the acid has been neutralized because the indicator has changed to a green color. The solid formed is calcium carbonate, and the calcium in the calcium carbonate came from the deer tooth. This is what the mixture looked like after I let it sit for a few hours. It kind of looks like fallen snow beneath a purple sunset. Gives me new appreciation for the term precipitate, you know? Okay, now we're going to filter the mixture to collect a solid calcium carbonate and weigh it. And from this weight, we can figure out how much calcium was in the tooth. That's because calcium carbonate contains 40.04% calcium by mass. All right, now that I've transferred the solid to filter paper, which I pre-weighed at 2.250 grams by the way, I need to collect the solid and pop it in an oven at just over 100 Celsius until dry. Come on, baby, it's the moment of truth. The mass of filter paper plus calcium carbonate is 4.681 grams. Subtracting the mass of the filter paper, this comes out to 2.431 grams of calcium carbonate. But don't forget, only 40.04% of calcium carbonate is calcium. If we take this into account, we see we measured 0.9734 grams of calcium in our deer tooth. And because the mass of the tooth I sampled was 3.043 grams, this comes out to just shy of 32% of calcium in the tooth. Now here's the deal. If the tooth was made of pure hydroxyapatite, we'd expect it to contain almost exactly 40% calcium by mass. So why did I get only 32%? The obvious answer is that teeth aren't 100% hydroxyapatite. They contain other material, like tough collagen protein, and this crazy undissolved brown-black stuff. Anyway, I gotta say it was pretty satisfying to estimate for myself how much calcium's in a tooth, but not nearly as satisfying as the chemical transformations I saw along the way. I need to take Ruby for some more walks.